So the last step of our example is trying to use generalized Fourier series to represent a continuous function which is in between the interval of a to b. Okay, so use Fourier series expansion to represent the continuous function fx. And let's just remind ourselves regarding the Sturm-Liouville problem example. We have minus y double prime equals to lambda y with homogeneous boundary conditions, which is y0 equals to 0, yl equals to 0. And we solve this problem first to get the eigenvalue and the eigenvectors. So we get our eigenvalues is equals to n squared pi square over L square. So this eigenvalue is a positive number where the n is equals to 1, 2, 3 until to infinity. And this is infinity infinite many eigenvalues. Each eigenvalue will correspond eigenvectors. So it will have infinity many eigenvectors as well. We have our eigenvector by n will be equals to sine n pi x over L, where by n is also start from 1, 2, 3 until to infinity. And you can see this is a sine function for your eigenvectors, and it satisfies for the Sturm-Liouville problem properties that the basis sites of your eigenvectors are orthogonal. So we also prove that this sine function is orthogonal basis. Yn, ym is equals to 0 when the m is now equals to n, and it is equals to L over 2 when my n is equals to m, so that my by n magnitudes will be L over 2 root. So those are already solved by our examples, and we have provide step-by-step analysis. Then the next part is now we are trying to use this orthogonal basis, which is a sine function, to represent any continuous function fx in between L 0 to L. Okay, so now any function fx when x is belong to a to b, where in our example will be 0 to L, satisfy f0 equals to 0, fl equals to 0, can be uniquely represent as fx equals to the sum from n equals to 1 to infinity bn yn, which is sine n pi x over L. And we also solve that the bn is equals to the inner product f yn over yn that is equals to 2 over L from 0 to L f times sine n pi x over L dx. So that is our bn, and really depends on what is your fx look like. Then you can correspondingly get your constant bn here. And you can write this fx continuous function as an expansion of the general Fourier series. Okay. So this is the generalized Fourier series expansion. And why the Fourier series is such important topic in engineering perspective, because a lot of spectroscopy you use for chemical engineering or chemistry or material science application, the generalized Fourier series expansion are the basis foundation for the spectroscopy. So some examples using Fourier transform. One is spectroscopy. For example, you can have Raman or FTIR or Zinse exactly those spectroscopy. Without Fourier transform, the spectroscopy won't be exist at the current technology. As we also said, quantum mechanics using Sturm-Liouville problem to generate the eigenvalue eigenvectors. The quantized energy level, we're using Fourier transform expansion as well. Some heat transfer problem we will talk later. 1D, 2D example using the partial differential equations for the heat transfer application also use Fourier series expansion. So there are many engineering perspective using Fourier series. That's why we need to understand this topic. We need to talk about this topic, and further, you probably need to analyze your topics using this Fourier series. Okay.